Hi, welcome back. In this video, we're going to set up a Riemann sum for the approximation of the area of a region under a curve. A Riemann sum is just a finite sum using n equal width subintervals, or n rectangles. So the curve we're going to use is one we've looked at before. We're going to find an approximation for the area under the curve f of x equals x squared on the interval from 0 to 1. And like I said, we're going to use n rectangles and right endpoints. So that means we're coming up with a formula, not an actual number. In class, we did the same region, but we used 4 rectangles and right endpoints, and we got a number, which was an approximation. Then we did it again using 4 rectangles and left endpoints. We got a different number, a different approximation. And then we did it a third time using 8 rectangles and right endpoints, and got a third number. And we noticed that when we took more rectangles, we got a better approximation. And so we kind of narrowed down the interval for the area. So what we're going to do, once we get a formula for the approximation using n rectangles, we're going to take the limit as the number of rectangles goes off to infinity, because that should give us the exact area. All right, so first let's set up the Riemann sum using n rectangles and right endpoints. So this is going to be called Rn for right endpoints and n rectangles. And so remember, it's just like what we did before. The width of each rectangle is called delta x, and the height of each rectangle is f of the right endpoint. So it's the y coordinate associated with the first right endpoint, so f of x1, and then times the width of the rectangle. That's the first area. And then the second rectangle has area f of x2 times the width, where x2 is the second right endpoint. And then we do it n times. And so there's n terms. The last rectangle has area f of xn times delta x. So xn is the last right endpoint. And so in sigma notation, we can write this as the sum as I goes from 1 to n of f of xi times delta x. All right, so our job now is to get an expression for delta x that depends on either I or n or both, and then get an expression also for xi, so we can plug that into the function f of x. And we need to get xi in terms of I and possibly n. So let's, it's always a good idea to visualize what you're doing. So here's the interval from 0 to 1, right? And we're chopping that interval up into n equally spaced subintervals. So what is the width of each subinterval? That's what our delta x has to be. So the width of each subinterval is going to be the entire interval width, which is 1 minus 0, divided by the number of subintervals, which is n. So delta x is 1 minus 0 over n, which is just 1 over n. So now I can rewrite my Riemann sum a little bit. So I've got the sum as I goes from 1 to n. Instead of f of xi, I can write xi squared, because that's what f does. And then instead of delta x, I can write 1 over n. All right, we're not quite done. We need to get an expression for xi. We don't want to leave it as just xi. We want to have an expression involving I and n. So let's look at that interval again. Each xi is a right endpoint, right? So the first right endpoint is going to be a distance of 1 over n away from 0. We just move over a distance of 1 over n. And then the second one, we're going to move over another 1 over n. And then we're going to keep doing that till we get to the last right endpoint. So what are these right endpoints? Well, the first one is just 0 plus 1 over n, which is 1 over n. The second one is 0 plus 2 times 1 over n. So it's 2 times 1 over n. And then we keep going, and the last one is going to be n times 1 over n, which is 1, which it should be. That's the last right endpoint. So let's list these and see what the pattern looks like. So x1, the first right endpoint, we said was 1 over n. x2, the second right endpoint, we said was 2 times 1 over n. The third one was 3 times 1 over n. And we see there's a pattern. So the I right endpoint, xi, has to be I times 1 over n. Or we could write that as I over n. So that's xi. So let's go back to our Riemann sum and rewrite it using that. So it's going to be the sum from 1 to n of I over n squared times 1 over n. And I can simplify that a little bit. So Rn is the sum from 1 to n of I squared over n squared times n. So that's, the denominator is just n to the third. So there's my Riemann sum. And that gives us a way to approximate the area under that curve using n rectangles and right endpoints. So now let's see how to get the exact area by taking the limit. So here's the definition we're going to use. The area under the region S that lies under the graph of the continuous function f is defined to be the limit of the sum of the areas of the approximating rectangles. So we're going to take the limit as n approaches infinity of Rn. Rn, remember, is the Riemann sum using n rectangles and right endpoints. So the Rn that we found was found to be the sum as I goes from 1 to n of I squared over n to the third. So we're going to take the limit. So A is going to be the limit as n approaches infinity of that finite sum. All right, so what we need to do is simplify the sum and somehow get rid of sigma so that we can use limit laws or L'Hopital's rule or whatever is legal, whatever works to get that limit. So the first thing we can do is use the distributive property, which is one of the first 5 properties we learned about finite sums, to get that n to the third out of the sigma. So I squared over n to the third is really I squared times 1 over n to the third. And since 1 over n to the third doesn't have an I in it, it's the same in every single term. So we can pull it out using the distributive property. So we get the limit as n approaches infinity of 1 over n to the third times the finite sum from 1 to n of I squared. All right, and now at this point we recognize, oh, the sum as I goes from 1 to n of I squared, that's the sum of the squares of the first n positive integers, and we have a formula for that. Theorem B on that handout with the properties of finite sums says that the sum as I goes from 1 to n of I squared is n times n plus 1 times 2n plus 1 all over 6. So we can get rid of sigma using that formula. So we can rewrite the limit as n approaches infinity of 1 over n to the third times n plus 1 times 2n plus 1 all over 6. All right. And now we know how to take this limit. So first I'm going to simplify a little bit so I can cancel that n with one of the n's in the denominator. And I can rewrite it as the limit as n approaches infinity of n plus 1 times 2n plus 1 over 6n squared. All right. And now I can, I don't need to multiply the numerator together. I could if I wanted to, but I can just go ahead and divide the top and the bottom by the highest power that appears in the denominator. And I get the limit as n approaches infinity of 1 plus 1 over n times 2 plus 1 over n. I just divided each of those factors by an n. And then the denominator, I divide by n squared, and I just get 6. And now we see that 1 over n goes to 0. And so what we're left with when we take the limit is just 2 over 6, or just 1/3. So that's the exact area under that curve on the interval from 0 to 1. All right, we'll be doing this a lot in the next section, and that's actually going to be our definition of a definite interval. All right, so I'll see you in some other video. I'm trying to make a video, little buddy. He likes Riemann sums. All right, little buddy. I gotta finish my video.